Hello, hello. Good evening, good day. How are you doing? I hope you're doing all doing great. Welcome to the latest episode of Ask Abhijit. Today we are discussing science, technology, and all of that good stuff. So before we begin, let me greet all of you. Let's see who all is there. I can see Aditya, Tulsi, Shweta, Gaurav, Crazy Brain, Saptarnab, Vishnu, Rahul, Srinivas, Dikshit, Jasmine, Vasu, Pranav, Krishna, Tanu's World, Bro, Lage Raho Online, Sparsh, Aditi, Shivam, Akshit, Gitu Parna, Vaishali, Roshan, R2, Pratham, Akhilesh, Balaji, Divyang, Avinash, Thinking, Herbie, Jetia, Gada, Pothul, Komal, Shubham, Rishikesh, Sketch with Sneha, um, Akash Rathor, Trupti, and lots of other people. Lots of other people. Good evening, good day, all of you, wherever you are. Great to have you all on the show. So, we will discuss science, technology, and related matters today. So, let us begin with the questions. And what is the first question? Right. The first question is appropriate for what's happening right now, the James Webb Space Telescope. So, lots of people have asked me questions about this. I've taken a few which represent all the questions, hopefully. So, Shweta says, how do you feel about analyzing the mind blowing images from the JWST? Any new findings, more details on the universe would be great. Amruta says the JWST showed the most stunning images, both awe-inspiring and intimidating. What are your thoughts as an astrophysicist? Do you feel we are really mature enough to understand these phenomena? Pratham says the James Webb Telescope captured in astonishing phenomena images. Can it really time travel? How do we do time traveling? Is it going back in time or going to a different location, running where the clocks are running slower than Earth, and so on? Yeah. So lots of people have asked me about this because it's something that's happened very recently. NASA has this week, I believe, released images, a bunch of images, 4 or 5 images that the James Webb Space Telescope has taken. The first batch of images have been released. Let's take a look at the images and let's see what they are telling us. So this is, let me, I hope you can all hear me. This is the Instagram account of the James Webb Telescope. NASA Webb is the account ID or whatever it's called. And as you can see, it has released a bunch of new images. I think there are 5 images. There is a spectrum of an exoplanet, and there's something more. So let's take a look at what the so what is the JWST? What is the James Webb Space Telescope? It's a new telescope. It's a much more powerful space telescope than the previous one that NASA had put up, which was the Hubble. The Hubble went into orbit, I believe, in the 1990s, if I'm not mistaken. The Hubble is still functional. It's in orbit around the Earth. The James Webb Space Telescope is not in orbit around the Earth. It's in orbit around the L2 Lagrange point, which is about 1 million, I think, kilometers from the Earth. So it's directly behind the Earth, as in a straight line with the sun. So if you take the sun and the Earth straight line, JWST is right behind that, about 1 million kilometers approximately from the Earth, roughly. So it's in the shade of the Earth. It doesn't see the sun. That's why it's cool. It stays cool. So this telescope, it is designed to remain extremely cool so that it can detect very cool infrared wavelengths, and that's why it's able to peer much deeper into space and essentially time travel. So let me get back to you after in a moment about what the time travel thing means. So this is one of the instruments. Okay, this is the spectrograph, the near infrared spectrograph. So this spectrograph, at a single time, it can take spectra from hundreds of targets at the same time. And as you can see, these lines, these horizontal lines are spectra. What is a spectrum? It's like a light signature. It's like a light library that comes from one source. What are the different chemical elements present in that light source, and so on? So that is something you can see from the spectrum. So this instrument can capture infrared spectra from hundreds of targets at the same time. So that's one of the great, very interesting and capabilities of the JWST. This is a new release. This is the spectrum, I believe. a spectrum of an exoplanet. So which exoplanet it is? It is the exoplanet WASP 96b, and it has detected the unmistakable, unambiguous signature of water, which indicates that there are clouds in this exoplanet. Now this is an exoplanet called a hot Jupiter. It's very close to its star. It uh, it orbits its star, I think, once in 3 or so Earth days. It's a very, very tight orbit. It's a very hot star, 1000 degrees, so, no, about 500, 600 degrees Celsius. I think the details are here. Yeah. And yeah, so it's been able to detect water in the atmosphere of this planet. That's interesting. This is a very interesting image. This is called Stephan's Quintet. 5 galaxies locked together. I think 4 of these galaxies are actually colliding at the same time. They are interacting gravitationally. This is a gravitational dance between 4 galaxies, and there's a fifth object as well in this. So 4 galaxies essentially colliding in very, very slow motion. This collision will go on for maybe over 1 billion years. Eventually, I believe there could be the output of the collision could be a merger and a new massive galaxy. So this is what that looks like through the lens, through the eyes of the James Webb Space Telescope. These are some images of Jupiter that the telescope has taken in infrared light, I believe. This is a very interesting image. This is the deepest, sharpest infrared image ever taken of the universe. And this, so what is, how do we put this image in context? So imagine you have a grain of sand, a single grain of sand. You put it in front of you and you look at the sky. The amount of sky that this one grain of sand is able to blot out, that is what is in this image. That's how small it is. That's how deep this telescope has been able to look. So this is nothing but a small fraction of the Hubble deep, ultra deep field, and it's able to look at this in unprecedented detail. Right now, what else do we have? We have this. I think it's called, what is this called? Cat's Eye Nebula, Southern Ring Nebula. It's a Southern Ring Nebula. It's a planetary nebula. This is what happens when a star dies. When a sun-like star gives off its outer layers of gas, this is what happens. Our sun will eventually meet this fate. So we still have the star in the center. It has given off all of its much of its outer layers. It became a red giant, and eventually the outer layers just went off because the star was not able to hold them together. So this is what happens. So this is unprecedented detail once again. And this is the cosmic cliffs part of the Carina Nebula. Once again, unprecedented detail. So now, how do we put these images in the right context is what we have to think about. So the best way of putting these images in the correct context is to compare them with the images that the Hubble Space Telescope gave us. So let me share that and let's do a comparison to understand the true power of of the new telescope. So this is a comparison, all right? The James Webb Space Telescope versus Hubble. So let me bigify this, enlarge, embiggen this. Yeah. So this is what Hubble showed us. Very interesting, nice image, lot of detail. And now see what the James Webb Telescope is able to do. Look at the extraordinary amount of detail the James Webb Space Telescope has uncovered. It's like a short-sighted person putting on glasses for the first time, and suddenly you can see the world in its real depth and sharpness. So that's how it is. So as you can see, the Hubble image, which I believe is in visible light, is quite opaque. The clouds are quite opaque. You can't really see through the clouds. But because the JWST operates in infrared wavelengths, it can peer through the clouds and see what's inside. And that's what you see in much greater depth, sharpness, and resolution. So this is the Carina Nebula. Let's see what else we have. So this is the other nebula that we spoke about. This is what Hubble showed us. Very nice image, very interesting. Now see what the JWST has done. Incredible detail. Incredible detail. We can see right through the clouds and see what's behind and see far more depth and resolution of this image. Then this is the Stephens quintet that we spoke about. This is what Hubble showed us. This is the Hubble image. Let me, yeah, now you should be able to see it properly. This is the image from Hubble. As you can see, the night sky is quite dark. We don't see much detail. And here we see way more detail. Look at that. We can see way more detail about what's happening here. So that's the amount of detail the JWST is able to show us. And this is just the beginning. This is just the beginning. This is the Hubble image of the ultra deep field. As you can see, a lot of detail, a lot of galaxies. But see what the James Webb Telescope has done. Incredible amount of sharpness and way more detail. And what you see here is these various galaxies that are all smeared out and squashed, and the shapes are distorted. This is called gravitational lensing, in which unseen matter, essentially dark matter, acts as a lens, as a just like an optical lens does, and it shows you what's behind and shows you things in a more magnified manner. And of course it produces distortion of light, because when you have a certain amount of massive amount of mass in space, light has to go around it. Light cannot travel in a straight line because the mass curves space-time itself, general relativity. So this is what you see. This is an exemplification of that, and so on. So these are the images from the James Webb Telescope. Revolutionary images, very great detail, unprecedented detail, and so exciting. We're gonna see. This is just the beginning. This is just a small sampler, amuse bouche. It's a starter before the main course, before the main meal. So this is the kind of detail this telescope is able to show us. Now, what about time travel? Why do some people say it's a time traveling telescope? It's not going back in time. What it is doing is this. See, when initially, in the initial moment of the Big Bang, all of the universe was just energy. And about 250 million or so years after the Big Bang, the universe first became transparent and light was able to shine for the first time. So that is the first initial light, the afterglow of the Big Bang, you could call it. Yeah. And that was very hot light. The universe was quite small at the time compared to to the size it is now. So the radiation, the afterglow of the Big Bang was high frequency light, hot light. As the universe expanded and cooled, the light was stretched out, it was red shifted, and the oldest light in the universe is now extremely, it's no longer visible. It's the CMBR, the cosmic microwave background radiation, is in the millimeter range. Yeah, that sort of those sort of frequencies, wavelengths, millimeter wavelengths. And the oldest light in the universe is redshifted so badly that it's undetectable to regular telescopes like the Hubble telescope and your backyard astronomy telescopes and so on. So in order to detect that ancient light, we need something like the Hubble or like the JWST. And to detect that, it has to be kept very cold, because infrared light is heat. It's heat, right? So it needs to be incredibly cold, and that's why it's been placed at the L2 Lagrange point in the shade of the earth, so that the sun's rays don't reach there. It remains cold, and that's why it's able to detect this very ancient and very faint and very cold light. And that's why it's going to be able to show us images, essentially what could be the first objects that were visible in the universe. The very first galaxies, the very first structure formation in the universe, and so on. That's why we say it's traveling back in time, because it's showing us images of the universe that are like more than 13.5 billion years old. So we are looking back in time. That's why we say it's a time traveling telescope. It's not really going back in time. It's showing us. It's going to show us pictures, images of the universe as it was a long time ago, in its very infancy. So that's why it's called, well, it's typically journalists who come up with these names: time traveling telescope, God particle, all that stuff. They're not scientific names, but yeah, these names catch on. Even the Big Bang was I don't know who came up with it. I think it was Fred Hoyle or somebody who coined this slightly derogatory name, but it stuck. And it caught on among the journalistic fraternity, and that's why it's part of popular imagination now. Anyhow, so that's a little bit about the James Webb Space Telescope. Looking forward to more data coming in. There's so much more science that this telescope is going to do. It's going to revolutionize astronomy, revolutionize hopefully our understanding of the universe, maybe throw light on so many hidden aspects. How was the universe in the very beginning? What is dark matter? Who knows? We may even get to understand that better. Understanding exoplanets, what they are like, the composition, the spectral composition, the atmospheric composition of exoplanets, maybe even some solar system astronomy, understanding Jupiter, Saturn, etc., our own solar system better. That also will happen, and so on. So it's just the beginning, a very exciting phase in astronomy and physics, astrophysics. Right. Question number 2 is by Shubham. Can green hydrogen be used as a fuel in the future? What are your thoughts on green hydrogen? All right, green hydrogen. So, first of all, my dear friends, let's understand this is not hydrogen that is green in color. All right, hydrogen is colorless, as far as I know. It is colorless, yes. What do you mean by green hydrogen? Green hydrogen is hydrogen that is produced using renewable energy, sustainable energy, which doesn't have a. So, essentially, the hydrogen that is produced without causing a carbon footprint. What do we mean by that? So, how is hydrogen typically produced commercially, industrially, etc.? It is produced via electrolysis of water. Water, as I'm sure you all know, is its chemical formula composition is H2O. Two atoms of hydrogen and one atom of oxygen come together to form the water molecule, H2O molecule, right? So if you have water, you pass an electric current through it, then you have a process called electrolysis, which dissociates the molecules into their component atoms, and that gives off oxygen and hydrogen. Now there are processes of separating these two things, and we need to be careful because hydrogen is a very flammable gas, and so on. So that's how it's done. And the reverse process happens in rocket engines. There are certain rocket engines which use hydrogen fuel and oxygen fuel. You bring them together, exothermic reaction, very enormously exothermic reaction, and the output of that is just water vapor, extremely high pressure, high temperature water vapor. Yeah. So electrolysis is the process of dissociating water into hydrogen and oxygen by passing electric current through it. That's what electrolysis is. Now, typically, electricity is produced by burning fossil fuels, either by burning coal or burning gas or whatever else. So, all electricity, most of the electricity that we use today has a carbon footprint. You need to release CO2, carbon dioxide, into the atmosphere to produce this electricity. However, if you produce electricity through renewable sources like wind power, hydropower, solar electricity, etc., then it has a what you could call a negligible or almost zero carbon footprint. So, if you take such electricity that is produced through sustainable means and you use that to produce hydrogen from water through electrolysis, that is what we call green hydrogen, because it doesn't have a carbon footprint, and we are it doesn't the production of such hydrogen does not cause harm to the planet. It does not add to the carbon burden of the planet in the atmosphere, right? So that is what we mean by green hydrogen. Now, hydrogen is a very good fuel. Very good fuel. It's used in rocket engines, so you can see how energetic it can be. Yeah, the specific impulse or whatever you call it is very high compared to fossil fuels like gasoline, petrol, kerosene, which is aviation fuel, diesel, and so on. So it can certainly be used, and engines can be produced which use hydrogen as fuel. So yeah, it's a promising fuel. You would need to tweak certain technologies in order to use hydrogen, maybe liquid hydrogen. I mean, there are challenges. Keeping hydrogen in the liquid state requires a lot of, well, it's a cryogenic fuel, right? Which means it's a very low temperature fuel. You need to refrigerate it to very low temperatures. I'm not sure what is the boiling point of hydrogen, which is the point at which its liquid form turns into gas, but it's a very low temperature. So to keep it liquid, you would need to have pressurized canisters at low temperatures, yeah, because the pressure is very high, and so on. So these are challenges, but yes, it can certainly be used if you develop the technologies. Developing technology typically takes a few years, and all technological uh, obstacles can be overcome with engineering. So I think if you can produce hydrogen in a sustainable fashion without adding to the carbon footprint, without adding to the carbon burden of the planet, of the atmosphere, then it's a very promising fuel. So I think it's a promising fuel. I think India is taking significant amounts of initiatives vis-a-vis green hydrogen. So I think it's great. India, I think it's essentially, in some ways, it's leading the world in moving to green technologies and sustainable energy sources. The Solar Alliance, India is the founding member of that alliance, and we have uh, we have stated that we will move entirely to sustainable sources of energy by 2070 or so, right? That's the statement that's been made. So I think we could be very much on track to do that. Takes time, but we need to develop these technologies step by step, and I think it's very promising. So yeah, so these are my thoughts about green hydrogen. Right. Aditi says, our body recognizes anything foreign that enters our body and starts to attack it. That's what the immune system does. Yes. But what about food? Food is also foreign, even though it's essential for us. Why doesn't our body attack it too? This is a very good question. This is a very good question. Excellent question. Good to see intelligent questions. Right. So you are right, Aditi, that you anything foreign, any foreign object that enters our body is immediately attacked. Let's say you are doing woodworking, carpentry, and a splinter of wood gets into your hand. It's very painful, very annoying, and you can see very quickly a reaction. The entire part of the skin around that flesh turns red, and there's a swelling, and then eventually, if you don't remove it, there'll be formation of pus, which is the byproduct of the immune attack on that system. And eventually the thing will be expelled, and the body, the that part of the body will heal itself rapidly. So that is the very visible immune reaction. Attack the foreign object. And as you say, food is foreign to us. So one of the examples of this immune attack on foreign objects is when somebody receives an organ transplant, a kidney or a heart or a lung or whatever it is, right? The immune system attack on these foreign objects, foreign organs, even though they are vital to your survival, is very true, is very real. And because of this very real phenomenon, people have to be given immunosuppressant drugs, entire cocktails of drugs, in order to keep the immune system, prevent the immune system from destroying that transplanted organ. Yes, so it is true that anything foreign that enters the body is immediately recognized by the immune system as something foreign, and it is attacked and it is destroyed. Take no enemies, destroy it. That's how it is. And yet we eat food. So why doesn't so what happens when we eat food? Okay, let's say I take a carrot. I don't have one right now for demonstration purposes, but let's say I'm eating a carrot. What do we do with the carrot? We put it in our mouth and we start attacking it right away. Chew, 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 chew. We chew it, chew it, chew it. Right? We chew it down, we mash it up, it mixes with our saliva, which has enzymes which break up the food. We swallow it. Inside our stomach, we have acid, hydrochloric acid, which further destroys that food and breaks it apart, right? And we have enzymes, and then it's transferred to our small intestine and large intestine. Everything of value is taken out of the food. It is totally destroyed, right? So isn't that what happens? So what is done is that anything that is potentially harmful in the food is neutralized. Let's say you eat a carrot that you have not washed. God forbid. The gods forbid. Don't eat a carrot that you got from the market. You did not wash it. You did not remove the skin, possibly. And maybe there are harmful bacteria on that carrot. You eat the carrot, you chew it up, all those bacteria will go inside. They will be taken care of by the immune system. Right? The immune system will neutralize anything. And sometimes when you eat something and there are too many bacteria or certain evil bacteria, salmonella, etc., then for some time you get food poisoning because they kind of overwhelm the immune system for a while before the immune system takes over and wipes them out. So anytime you eat food, all the same immune responses happen. Every molecule of the food is scrutinized by the immune system, and it is checked. Its passport and visa is checked. Essentially, do you have anything harmful on you? A thorough screening is done, and only when it's just in just molecules and proteins and phytochemicals and all those things, only then is it allowed to pass through. If something harmful is there, it is destroyed, annihilated, neutralized, right? So yes, the same checks are done even when we eat food, but there's a whole different system. We don't take a sliver of carrot and we don't put it into our flesh. We send it through the right uh, in the right way, right? Through due process. The due process is to put it in your mouth and to swallow it and chew it, swallow it, have it digest, and so on. So if you do it through the due process, through the proper approved procedure, then the proper checks and balances are done. But if you take a piece of carrot or apple or whatever and you shove it into your skin, it will meet the exact same immune response as a sliver of wood would meet. And similarly, if you eat wood, you chew it properly, or you take sawdust and you eat it, it won't meet the same immune response as it would meet if you were to shove it inside your palm, right? So the immune system, of course, has all the same checks and balances. I mean, the digestive system has all the same immunological checks and balances. The immune system takes very good care to ensure that nothing harmful gets into the body, either through the stomach lining, or through the esophagus, or through the lining, alveolar lining of the intestines, and so on. At every single step, there are checks and balances. Everything is taken care of. So that's how it works. It's a very interesting, complicated process. Even biology is incredibly fascinating. Incredibly fascinating. So yeah, that is in brief the answer. It's a very intelligent question you asked. It's good to see that. Good job. Okay, Balu says, what do you think about the future where we will be living in the metaverse? Well, that is still to be seen whether we will be living in the metaverse. The metaverse creators would like us all to live in the metaverse. So, what is this metaverse thing? What is it? The metaverse is this imaginary world which we can access through virtual reality headsets, those bulky things that you wear on your eyes, and then you go into a different world. And then they want you to live there for hours and hours and hours and purchase real estate that is imaginary, and essentially live in this augmented reality. So right now, the virtual reality headsets that are available via various metaverse creating companies. So who are these creators of the metaverse? There are like, it's a bunch of extremely large, extremely powerful, and extremely wealthy corporations, all in the US, who want to change the world. They want to change the world. They want to change the way we live. They want to change our lifestyles. They want to change the way we interact with data, with information. They want to change the way we spend our time, all of that. That is the metaverse. So one of them is Meta. They have changed their name from Facebook to Meta, in to be in line with their push towards in this coming decade to make the metaverse a reality. So the metaverse is virtual reality and augmented reality. So right now, the headsets that you have to wear are very bulky. You wear that for more than an hour, I think you would get a headache. It's that bulky. But they are working on the technology to make it lighter and lighter. Eventually, it will be just like wearing glasses, right? So you wear those glasses and you will see the same world, but you will see augmented reality. So you will see extra data on that. So right now, you just see a few books around behind me over here. You can see that you wear those glasses, each of and you can choose any book. Let's say this blue one here, and I do something, and it will show me right away without opening the book who's the author, how many pages, how many words, etc., etc., etc. Metadata. That is one example. You go for a walk wearing those VR glasses, and you will see information about every single store. What is the store about? How long has it been open? What is the average monthly income that they make, or and so on. So is there anything that is of use to you or of interest to you? It will show you all of that. So you don't have to go and talk to people anymore. You will get all the data right away. That is one example. The other thing is living in virtual reality. You have games like Minecraft, which is a virtual illusionary world. You have games like platforms like Roblox, and so on. You have role playing games in which you immerse yourself in that environment and you become a warrior or something. So eventually they would want this to be available at your fingertips tips on demand. And eventually that would you would not even perhaps need glasses for that. You may use contact lenses, or eventually even neural implants to have that on demand, as long as you pay the monthly subscription. Eventually you may even get custom designed dreams if you wish, or whatever. So all of this is the metaverse. It's something that they it's an artificial virtual world that they want to superimpose on the current world. And obviously the thing is this, they are how they want to sell it is by showing us the good effect of that. Like, you can sit at home and pretend like you're in office and talk to your colleagues as if you're in the same room, but you're actually in your bedroom or in your office at home or whatever, right? That sort of thing. So you no longer have to go to office. You can be like you're in the office, and you will have virtual avatars that represent you with your real face, and you can talk to your colleagues, etc., and work together collaboratively, and so on. There are obviously problems right now, like the time lag when it comes to internet communication and so on, but they are working on these things, and eventually they would want to solve all these problems. So they are saying that it makes it easier for you to work. We will make it happen. It will be much easier for your kids to learn. Kids could be at home and still be in school. They could read books on demand. They could learn information sitting at home and so on. But the real monetization, the real commercial value is in the games and all that. So essentially they would like to hook kids into this. They would like to hook kids into the metaverse. It is easier to form habits as when you're a kid, as opposed to when you are much older, which is why you will see uncles and aunties, no offense, you know, people who are 40 plus, etc., who will not be really interested in the metaverse, but people who are teenagers essentially, or even kids in their first decade of life, they take up technology so easily, like fish to water. It is this specific cohort, this specific generation Z, that they want to hook into this, which is where the commercial value lies, because they will be able to eventually monetize everything, commercialize every single aspect of the metaverse. You can even buy virtual real estate in the metaverse now. So that is what the future is. I don't think it's necessarily a very good thing. The real world is the real world. That is the real physical world we live in. We can pretend like we're in a virtual reality and pretend like we are superheroes and all, but at the end of the day, if you spend so much time in some illusory world while sitting in a dark corner of your bedroom on a blanket, you're gonna neglect your health, and you're gonna have shorter and shorter lives, and it's not gonna be good for you. You're gonna have mental issues, emotional issues, whatnot. So I don't think it's a good thing. They want to enrich themselves at the expense of the rest of the world. I don't think it's a good thing. Technology is a double-edged sword. Uh, it has good applications and applications that are not good for everyone. So even the metaverse is the same thing. There are pros and cons, but that's what it is like. The battle is still to be fought. Right now, the technologies are still in their infancy. But by the time this decade is out, the technologies will have developed. They will have matured, and they will be like, well, very attractive to people. So let us see how it goes. But I think it may not necessarily be a very good thing for everybody. It will be certainly good for the corporations, but for the rest of the world, not so convinced. Tejas says, how do we see viruses under electron microscopes when viruses are smaller than the wavelength of light? For us to see anything, the light must reflect back from the surface, right? Does that mean electrons behave the same way as light? This is a good question. So, what is light? What is all that? So, light is photons. Visible light has a certain wavelength. And as Tejas says, viruses are extremely small particles that are much smaller than the wavelength of visible light. So, how does this work? So, even see, you must have heard of something called quantum mechanics, wave particle duality. Every particle can behave like a wave. Every wave can essentially have a particle nature, and so that way, even the electron, which is essentially a point particle of sorts, it has a wavelength. We know what the mass of the electron is, and we know what is the very simple formula for the wavelength of a massive particle. Lambda is equal to h over p, where h is the Planck constant, p is the momentum, which essentially means that lambda is the wavelength. So lambda is equal to h upon mv. Lambda is the wavelength, h is Planck's constant, m is the mass, v is the velocity, right? And if you fire electrons at a certain speed, at a certain velocity, what you find that the wavelength of these electrons can be around 100,000 times shorter than the wavelength of visible light photons. 1 lakh times shorter. So that way, the resolution of the image that you will get out of this is 100,000 times uh, better. And that's why we're able to see viruses under these by using electrons instead of photons for probing the surfaces, for probing the surface of the virus. That's why we are able to get good images in electron microscopes. So what the electron microscope does is that it fires a beam. I see. I don't know if the exact engineering mechanics and the way electron microscopes are built, but I know it conceptually from the perspective of physics. So what you do is you fire a beam of electrons at the target, right? Those electrons, I suppose, reflect back, and you would get a reading. And based on the reading, you can create a map of the object that you're trying to probe. And that map essentially is the image that you see with your eyes. So that way, you can see things that visible light can never ever show you, because you're using electrons as waves, not as particles, as waves. So, yes, electrons do behave the same way as light. The photons are packets of energy, they are particles, and they are also waves. They have frequency and wavelength. Similarly, electrons also have frequency and wavelength. This is the quantum wave particle duality in action, in real action. We actually use that in technology. Electron microscopes are a great example of that. So it's not light, it's electrons. It's electrons used as light. And that's how we're able to see things that regular visible light would never ever show us. That's in brief how it works. Karun says, what will be the fastest future transports and ways to travel in space after maybe a half a century or 100 years? Can we achieve the speed higher than 10,000, 100,000 kilometers per hour for traveling? And what are your views on Jeff Bezos' anti-aging startup being immortal is really possible? Okay. So what is the speed of light? 300,000 kilometers per second. Yes. 300,000 kilometers per second. You're talking about 100,000 kilometers per hour. So that is much slower than that. Is it possible? Yes, it is possible, and this could happen soon, I suppose. There is this project called Breakthrough Starshot, which is going to use light sail technology to, and the objective is to have a large number of small spacecraft, micro spacecraft, maybe just a small little thing, which will have a light sail, and it will have a very small chip that will with the optical sensors, etc. You're going to use pulsed laser light. You're going to shine this laser light on the light sails, and these micro spacecraft, there may be thousands of these, will be accelerated using radiation pressure of the lasers to a speed that may be maybe a third of that of light, maybe one third light speed. And using this incredible speed that we'll be able to achieve, we will be able to send this entire massive armada fleet of spacecraft, micro spacecraft, to our nearest neighboring star system, Alpha Centauri, Proxima Centauri, and we could have these spacecraft visit one of the exoplanets that's known to be in orbit around the system. And so this process will take 20 to 30 years, maybe 40 years. Within 30 to 40 years, these spacecraft traveling at nearly a third of the speed of light will be able to reach our neighboring star in just 30 or so years. And then they will take images, data, etc., photographs, etc., and beam it back to Earth, which will take about 4 years, 4.5 years. So within half a century, we will have actual images of an exoplanet in our neighboring star system, which is about roughly 4.5 light years away from here. So this is possible. The technology almost exists today. The phased laser array, etc., needs to be worked on. But once that technology is available, we will be actually able to do that. So this could happen within a decade. Within a decade, we will have spacecraft, tiny spacecraft, that can be accelerated to nearly a third of the speed of light. or something like that, roughly. Yeah, relativistic velocities. So this is a technology demonstration on a small scale. When you are building a fighter plane, you first develop a small model, which is an exact replica of what the large thing will look like. You test it in a wind tunnel and you check out how it works and so on. So that is a technology demonstration. Using that, you can improve upon it, upon the design. So similarly, this is going to be a technology demonstration on a small scale of tiny spacecraft, tiny little spacecraft, micro spacecraft. But the same principle will work just as well on large spacecraft with massive light sails, kilometers, square kilometers in size. But you would need much more powerful lasers to accelerate such large spacecraft to relativistic velocities. So in the next 100 years, definitely possible. Yeah, traveling at relativistic velocities is definitely possible if we're able to develop the technologies needed for that. Essentially, powerful enough lasers. Very much possible. So that is your answer. And what about Jeff Bezos' anti-aging startup? Is being immortal really possible? Being immortal, as far as I understand, is not possible. You can certainly extend the lifespan of human beings. Right now, the in developed countries, the average life expectancy is around 80, 80, 82, 83. In Japan, I think it's 83, 84. It's between 70 to 85 years, something like that. In developed countries, in other countries with lower living standards, you have lower life expectancy, and so on and so forth, right? So it is certainly possible to extend the lifespan of a human being using various processes. I've spoken about this before. It seems to be that aging, the process of aging, is caused by the shortening of telomeres at the ends of human chromosomes. So a chromosome is essentially something that carries part of your DNA, part of your genome. At the ends of your chromosomes, inside your body, inside your cells, you have something called telomeres. Now, as a person grows older in years, the length of the telomeres at the ends of the chromosomes, it gets shorter, and this seems to be intrinsically connected to the process of aging. So it is theorized that if you can stop the shortening of the telomeres, then the process of aging can be possibly retarded, slowed down, possibly even stopped, possibly, we don't know. So there are some startups working on that, and if I'm not mistaken, maybe Jeff Bezos and his startup is also working on this particular theory, that if you can stop the shortening of the telomeres, then you can possibly stop aging. I don't think it would give a person infinite lifespan. I don't think so. Maybe you could add 10, 20, possibly even 50 years to the human lifespan if you can get this done well, if you can make this work. It may also lead to improvements in brain health, possibly things like dementia and Alzheimer's disease, etc. Could possibly be treated or even prevented with this. We don't know yet. So this research is still, you could call it, in the initial phases, initial stages, possibly in its infancy. So I think it is certainly going to be possible to extend human lives by maybe 10, 20, 30, possibly even 50 years. Being immortal, I think it's impossible. Immortal means infinite, and infinity is unphysical. What is an infinity? It's division by zero. That's unphysical. So I don't think it would be possible ever to have an infinite lifespan. Yeah. But yeah, an extension of human lives is certainly possible in terms of years. So yeah, it's something they're working on. Okay, Karan says, is it possible to make antimatter weapons? Antimatter weapons. So that's interesting. So what is antimatter? I think we deal with a lot of antimatter these days on this show. What's antimatter? Antimatter particles are the they are the same. They have the same mass as their regular matter counterparts, but they have opposite charges. Like, for instance, the positron, which is the antimatter equivalent of the electron, has the same mass as the electron, but electrons have negative charge, positrons have positive charge. Antiprotons are again the same thing, the same mass as regular protons, but opposite electric charges, and so on. So that's one way of looking at antimatter, right? So antimatter has been produced in various linear colliders, atom smashers like the LHC, etc. Yes, it is certainly possible to create antimatter. And the thing about antimatter and matter is that if antimatter comes into contact with regular matter, it immediately annihilates. So let's say one anti-hydrogen atom comes into contact with a regular hydrogen atom, there is going to be an immediate annihilation, and all that is released is pure energy. Pure energy. So that's what it is. So let's say you have 1 gram of matter and 1 gram of antimatter, and you are able to get these two grams of matter antimatter to annihilate completely. It's going to give off about 10 raised to 14 joules of energy, and its equivalent is about 40 to 45 kilotons equivalent of TNT. What does this mean? 40 to 45 kilotons equivalent of TNT. Comparison: the Hiroshima nuclear disaster with the Hiroshima nuclear weapon gave off a yield of 15 kilotons equivalent of TNT. 15. The Nagasaki event, the Nagasaki war crime, it gave off a yield of about 21 or 22 kilotons of TNT. Hiroshima, 15 kilotons. Nagasaki, 22 kilotons. 1 gram of matter, 1 gram of antimatter annihilate, you get about 40 to 45 kilotons of TNT. Just 1 gram plus 1 gram. So 2 grams. So for this, you just need 1 gram of antimatter to react with 1 gram of regular matter. Regular matter is abundant. We don't need to seek it. We don't need, it costs nothing. But antimatter is the real deal. So you have 1 gram of antimatter. You can produce the enough energy, the energy equivalent of, let's say, around 3 Hiroshima nuclear weapons, right? So that is the amount of energy it can give off. So yes, if you have antimatter at your disposal, you can make incredibly powerful and energetic antimatter weapons. You can do that. The question is, do we have a means of producing antimatter? Like I said, linear colliders and atom smashers like the LHC, like the Large Hadron Collider, etc., they produce antimatter on a regular basis. Antiparticles. Yeah. So that's what happens in these atom smashers and linear colliders. But the amount of antimatter that we are able to produce is negligible, very, very less. I think anti-hydrogen has been produced, and it's very difficult to store antimatter. You need to keep it in almost perfect vacuum, because if you keep antimatter in air, in the atmosphere, it will react with the molecules of air. It will annihilate immediately. It needs to be in complete perfect vacuum, and it should. We also need to ensure it doesn't touch the walls of the container which has this vacuum. So you need magnetic confinement and all that, and it's very difficult to produce any significant amount of antimatter. So it's extremely expensive to do that. So the Manhattan Project in the 1930s and 40s, which produced the first nuclear reactor and the first nuclear weapon, its budget, it cost about $30 billion in today's money, approximately $30 billion in today's money. Now, a millionth of a gram of antimatter, a millionth, 1 divided by 1 million, that much of a gram of antimatter would cost about $60 billion today. 6 with 9 zeros at the end of it. A thousandth of a gram of antimatter would cost about $60 trillion. 6 with 12 zeros after it. And a single gram, 1 gram of antimatter would cost about $60 quadrillion. 6 with 15 zeros after it. So as you can see, nobody has this sort of money. The amount of money that you need in order to produce just 1 gram of antimatter. And that's why, even though it is certainly possible, it's impractical today. In the future, we may have the technology to produce more antimatter at a smaller cost. Maybe it could cost the same as a nuclear weapon. In that case, it would be as financially viable as building nuclear weapons, and it would offer significant advantages over nuclear weapons and so on. But as of today, it's prohibitively expensive to produce any reasonable amount of antimatter. Just 1 gram will cost quadrillions of dollars, right? So that's why it's not possible today. That's why it's impractical to do it today. Possibly, is it possible? Certainly, it is possible. It is certainly possible, but that won't happen in the near future, anytime in the near future. Maybe in the next 50 years, maybe in the next 100 years, possibly we may have it. In that case, we could even use antimatter as rocket fuel. Yeah, if we can produce sufficient amounts of that, that would be an extremely useful rocket fuel, extremely efficient and effective rocket fuel. So yes, theoretically possible, physically possible, but practically, but from the perspective of practicality, it's extremely impractical today. In the future, it may happen. Aditi says, how does evolution take place? What causes our biology to evolve, our journey to becoming Homo sapiens? How does it take place at the atomic level? Please give your views on the ancient girl who was an interbred of Neanderthals and Denisovans. Is interbreeding possible today, and do there still exist these species in pure form anywhere, somewhere in the world? Right. So, what is evolution? Evolution is a very slow process. It's a very, very slow process. It doesn't happen over a period of weeks or hours or months or years. It happens over hundreds of thousands of years. So, Homo sapiens, our species, has been around for about 300,000 years. We have found fossils in parts of Africa, I think in northern Africa, of Homo sapiens that date back to almost 300,000 years before today, 3 lakh years. Same species as us, anatomically modern human beings. They were not different from us from the anatomical perspective or the species perspective. They were the same species. So our species is at least 300,000 years old. And as you can see, so that's the kind of time scale it takes for evolution to happen. Before that, you would have a more archaic ancestral form of Homo sapiens that we don't quite know what it was like, but it would be like more primitive, not more primitive, but different from the evolutionary perspective. You go back 1,000,000 years, you have various more archaic human species. You go back about 3 or so million years, you have the ancestors of humans and chimpanzees. You go back 6 million years, you have the ancestors of humans, chimpanzees, and gorillas as well. So evolution takes place on very long time scales, right? How does it happen? It happens through natural selection. So it's essentially a very slow response to the environment. Uh, when a child is made, it is the combination of genes from both parents, right? It's a combination of genes from both parents, and typically what happens is that the mechanism, somehow it's not quite well understood how it happens, but it tends to take the most advantageous traits from both parents. Sometimes you get bad traits as well. I mean, if somebody has some genetic defect or some inherited illness, that also gets passed on, right? There are lots of things like hemophilia and whatever else, right? Asthma, leukoderma, whatever. So certain recessive or disadvantageous traits are passed on, but typically over long periods of time, what happens is that the people in whom disadvantageous traits are passed on, they don't survive. These are disadvantageous to your survival. So over hundreds of thousands of years, the genes that are disadvantageous to your long-term survival get weeded out in the evolutionary process, right? And the more advantageous genes are passed on, because the people who typically are healthier have more children, and those traits are passed on. So it's a very long process, very slow process, and it does not happen at the atomic level. It happens at the genomic level, at the level of your DNA and your chromosomes. So it is there that this happens, and the actual physical process is the process of combination of genes from both parents. That's how it happens. So that is it's very hard to give a clear idea uh, without going deep into molecular biology. But that is overall how it happens. Very long time scales, very slow process, it happens over thousands of generations, that certain genes are weeded out because they are disadvantageous to the long-term survival of the species. And what happens is that typically over long periods of time, the species adapts in such a way that it responds best to the environment. So let's say you are living in a very long ice age that has been going on for 200,000 years. Slowly the species, you will see, it will develop more hair, more fur, because that gives it an advantage. Oh, and it helps it survive more in cold climate. So that's the sort of response you see over long periods of time to the climatic and environmental conditions. We know that our very deep ancestors, very ancient ancestors, were fish who lived in the oceans. Eventually, for whatever reason, they emerged out on land. And slowly, over millions of years, they developed what's called lungs. They developed the ability to breathe oxygen and survive entirely on land. This happened over several millions of years. These are very slow, uh, iterative responses to the environmental changes and lifestyle changes. So that's how it happens. It's a very slow process. Now, what about this girl who was, like you say, interbred Neanderthal and Denisovans? So when it comes to the Neanderthals and the Denisovans, these are subspecies of so you have Homo sapiens, Homo neanderthalis, Homo denisovan, or whatever it is. Uh, these are subspecies of human beings. Just like, let me give you a very crude approximation. We have wolves and we have the regular dogs. Canis lupus and Canis lupus domestic, whatever the Latin name is. So the domestic dog that we have is a subspecies of the wolf, of the wild wolf. They are essentially the same animal, the same species. But the domesticated house dog, or the dog that lives with humans, is a subspecies of the wolf. They can still interbreed and produce very viable offspring. So what would you call them? Dogs, wolves? Doesn't matter. It's just a canine species. That's a very crude and rough example, for analogy purposes. Now, when it comes to humans, Homo sapiens, or Neanderthals, Denisovans, we are we know that the Neanderthals went extinct about 20, 30,000 years before today. Denisovans also went extinct for whatever reason. And yet we know that there was interbreeding between Homo sapiens and Neanderthals, and Homo sapiens and Denisovans. And also now we know between Neanderthals and Denisovans themselves. So the species, these three different kinds of humans, were were genetically close enough that they could breed with each other and produce viable offspring. We know that most non-African human beings have about 4-5% Neanderthal ancestry. We know that certain populations in Asia, in Oceania, etc., human populations have maybe 2-3-4% of Denisovan ancestry, and so on. And there is some back reaction into Africa as well of Neanderthal ancestry. It's a very complex genetic landscape. Uh, so this interbreeding was possible because these species or subspecies were genetically close enough, which means that their last common ancestor was quite recent, which means that they had not completely diverged to the extent that they could not interbreed and produce offspring. Humans and gorillas, or humans and chimpanzees, cannot produce offspring even if they were to try. And similarly for gorillas and chimpanzees, etc., because it's been so long that the genetics have diverged significantly. It's no longer possible to produce offspring. But among these three species, subspecies, humans, sapiens, Neanderthals, and Denisovans, it was possible. And that's why you see that I believe in India we don't seem to have much Neanderthal ancestry for whatever reason. That's a whole different story. The Aryan invasion, migration, tourism, picnic myth. But yeah. So interbreeding is possible. Well, we no longer have Neanderthals. We no longer have Denisovans. We only have Homo sapiens now. I don't know how it happened, but we are the only ones left, and we are all over. So how do we interbreed? It's not possible because we don't have any of them to interbreed with. And so yeah, that's your answer. These species don't exist, and there is no such thing as a pure species. A pure species It doesn't make any sense. There is no such thing as a pure species. There is no such thing as a pure race. People talk about races of human beings. That's a It's an extraordinarily unscientific idea. So yeah, those species or subspecies no longer exist, and there is no such thing as pure species, and so on and so forth. All right, so that's the answer. Akash says, I read that black holes have three properties: mass, charge, and spin. But black holes are just a tear in the space time fabric. So, what does it really mean that they spin and have a charge? Also, connected to this is, what is a Schwarzschild black hole? And how do we find out the mass of black holes when we can barely see them? All right. So, black holes are not quite tears in the fabric of space time. They're not tears or holes in space time. A black hole is essentially a mass, a pure mass. That's what it is. So let me first go to what is the Schwarzschild radius and all that. So what is a Schwarzschild black hole? It is an uncharged, non-rotating black hole. That is what a Schwarzschild black hole is. So the Schwarzschild solution to the Einstein field equations is something that is uncharged and non-rotating in a universe without a cosmological constant. That's the Schwarzschild metric, a solution to the Einstein field equations. Then you have other kinds of black holes like the Reissner-Nordstrom black hole, which is a charged black hole, but it is not rotating. Then you have Kerr black holes, which are uncharged black holes that are rotating, that have angular momentum. And then you have Kerr-Newman black holes that are charged as well as rotating. These are different solutions to the Einstein field equations, to the Einstein-Maxwell equations, and so on, which give us these different kinds of black holes. So black holes can come in these different flavors: uncharged, non-rotating, which are Schwarzschild black holes; charged but non-rotating, Reissner-Nordstrom; uncharged, rotating, which is Kerr; and charged as well as rotating, Kerr-Newman. 4 different major flavors or types of black holes, right? So what is a black hole? A black hole is a region in space-time that conceals a point. From the general relativity perspective, it's a region in space-time that conceals a point that has infinite density, mass density, and infinite curvature. And this is hidden behind what's called an event horizon. So it's not a tear in the fabric of space-time, but it is something unphysical. An infinity is unphysical. What is an infinity? You divide a number by 0, that's when you get infinity. That is unphysical. That cannot happen. So that tells us that there is a flaw, a defect in the physics, in the equations of general relativity. We need a better theory of relativity. We need a theory of relativity that brings that is a marriage between geometrodynamics of Einstein and quantum theory, quantum field theory, quantum mechanics. You combine the two, you will have a proper theory of quantum gravity, in which I believe these singularities will no longer occur. So from what we know today, a black hole is a regional space-time. Yeah, it is an event horizon which conceals, which hides this monstrous singularity. It's not a tear in the fabric of space-time, right? So that is what it is. So we also have something called an extremal black hole. So an extremal black hole is an object that has the minimal possible mass compatible with a given amount of charge and given amount of angular momentum. So that's an extremal black hole. And you have near extremal black holes, etc. It is speculated or hypothesized that theorized that the entropy of an extremal black hole could be equal to 0, and so on. Now the other question is, how do we find the mass of black holes when we can barely see them? Very simple: Newtonian mechanics, Newtonian dynamics, celestial dynamics. You see the effect the black hole has on other objects. If you see a star, let's say you're talking about the star, the black hole, the supermassive black hole at the center of our own galaxy, the Milky Way. We know where it is. We don't see it. It's dark. But what do we see? We see this incredible dance that the other stars in this region are doing around this invisible object. We see the speeds, the velocities of the stars. Yeah, these are elliptical orbits. We can deduce the size, the masses of the stars through various means, astronomical techniques. So we know there's a bunch of stars at the very heart of our galaxy that are doing this extraordinary dance around an unseen object. And based on the size, distance, speed, and time of the orbits and the masses of the stars, we can very accurately deduce the mass of this unseen object that is making them all dance around. So that's one way of deducing the mass of a black hole. And there are other ways. You can use gravitational lensing. A black hole is invisible. Yeah, it's dark, invisible actually, but it is a very massive object which causes light to warp around it, which causes space time to warp around it, the warping of space time. And that's why light bends, and you can measure the bending of the light and calculate the amount of mass a black hole would have. So there are multiple ways of doing it, and that's how typically it is done. Okay, Dhruva Kumar says, is the placebo effect real? How can anyone treat their diseased body without medicine? What's your take on this? The placebo effect is something that you see in medicine. So let's say you're doing a trial of a new drug. You have come up with a new drug to treat some illness, yeah? And you want to do a trial. So how do you do a proper trial? You take two groups of volunteers. Let's say a group of 100 here, and a group of 100 there. You call one group A, and you call one group B. Total 200 people divided into two groups, A and B. To group A, you give the new drug that you've developed let's say in the form of a pill, a white pill. So that is what you give to the 100 people in group A, this white pill, which is the new drug that you've developed to treat whatever illness. In group B, so both these groups of people have that illness, okay, which this drug is supposed to treat. Group A takes the drug. Group B, you give the same kind of white pill, but it is an inactive substance. It doesn't contain the drug. It doesn't contain the medicine. It is nothing. It's an inactive. It's gelatin or cellulose or whatever, something that will not react with the body. It will do nothing. But you don't tell these two groups what they've received. So both will believe that they have taken the drug. And then over time, over the very specific period of time, you see the kind of effect these two groups exhibit. And that's how you can see whether a drug is efficacious or not. So the tablet which contains the drug is the actual drug, and the tablet which does nothing is called a placebo. And very often it is seen that when you give a person a placebo and tell them it's a drug that is going to treat you and cure you of whatever, it actually happens. It actually works. So the placebo effect is real. Let's say somebody is suffering from a headache. You tell them this take this pill, you'll be fine in 30 minutes. Often, even though the pill contains nothing, the headache kind of resolves within 30 minutes or so. Sometimes a person may be feeling lethargic, and you say that take this caffeine pill and swallow it. Within 20 minutes, you'll feel much more active and vigorous, and it's placebo. Very often you see that the person actually feels much better after taking a placebo. So this is called the placebo effect. It cannot actually treat diseases. It cannot cure you of cancer. It cannot cure heart disease, but it can have certain effects, certain very beneficial effects. Sometimes even when a person knows that they're taking a placebo, you may see this kind of effect. So that's what the placebo effect is. It is like, so it's because in certain cases, the mind, the brain, or whatever you want to call it, it has the ability to produce significant beneficial biochemical changes in the body, which may end up giving you a better outcome to whatever problem you're suffering, right? For instance, the brain is capable of releasing endorphins, which are natural painkillers. Endorphins. You give a person a placebo, say it's a painkiller, it may induce the brain into releasing endorphins that have the same effect as a painkiller, and so on. So that is what the placebo effect is. It is not very well understood. It is known to work, and it's one of the great mysteries of the human brain, the human psyche, the subconscious, and so on and so forth. Ayush says almost all of the ed tech views show space-time curving below a planet or a star, just like a trampoline. But there is no top or bottom in space. Then does it mean that space-time curves in all directions around a planet or star? Or a star? And if so, then how can a black hole have infinite curvature of space-time in all directions? Good question. So yes, you see any popular science TV show or documentary, etc. They will show you a trampoline-like surface in which you place planet. Let's see it. It's all over. Um, Let me share my screen and let's pull out one of these images. Take a look at this. Take a look at what they do to us. See, this is your typical, this is the way they show it typically. It's a two-dimensional surface with length and breadth, which with this grid structure on it, this grid etched on it, you place these planets or massive objects and you see how space-time curves. So this is how they show the curvature of space-time. And the question which Ayush is asking is true, is a good question. It's always shown this way. Does it mean that there is top and bottom in space? Well, it is not true. This is a misleading representation of the curvature of space-time. Let me show you a true, more accurate representation of the curvature of space-time. Take a look at this. This is how space-time actually curves. Let me remove this from here. Take a look. This is what space-time curvature should be shown as actually. So it curves in 3 dimensions. The presence of mass makes the fabric of space-time, the 4-dimensional fabric of space-time, to curve in this manner. What we are seeing is the curvature of the 3 spatial dimensions: length, breadth, and height. We cannot see the curvature of time, obviously, because we don't have the ability to see in 4 dimensions. But this is what the real curvature of space looks like when it is affected by mass. So it is not this sort of curvature, 2-dimensional curvature. It's a 3-dimensional curvature of space-time. So remember this meme. This meme, you should remember that the 2-dimensional view is misleading. It is incorrect. The 3-dimensional view is what the curvature of space is really like. All right. So that's what it is. That's what the curvature of space-time really is like. That's how you should visualize it in your mind's eye. What's the other question? Infinite curvature. Yeah, infinite curvature is unphysical. It doesn't make sense. So from the perspective of general relativity, from the equations, from the solutions of the equations, it's telling us that at the heart, at the very center of a black hole, behind the event horizon, unseen from the mortal eye, at the very center of this black hole, of any black hole, there is a point of infinite space-time curvature and infinite density. Infinity. But infinities are unphysical. How do you mathematically create an infinity? You take a number and divide by 0. You take 1 divided by 0, it's infinity. You take a million divided by 0, it's infinity. You take any number, divide by 0, it's infinity. That is unphysical. It simply cannot happen in the real world. So what it means is that general relativity is flawed. It is incorrect. It is very accurate. It has passed all tests that we have been able to throw at it. But at the microscope, at the ultra microscopic level, it breaks down. The equations give us unphysical answers, singularities, infinities, which means that the theory works great at macroscopic scales, at large scales, but it breaks down at the ultra microscopic quantum scale, which means that we need a better version of this theory. We need a quantum theory of gravity, quantum gravity, and we still don't have it. So that's what it is. Karthik says, are the conscious mind and the subconscious mind real? Can you please differentiate between them? Yeah, there does seem to be a conscious level of existence and a subconscious level of existence. Conscious mind, subconscious mind. The conscious mind is what we use in doing things consciously, deliberately, when we are thinking about something, when we are doing decision making, when we decide what to do, when we are learning, when we are practicing some skill, we are doing it consciously, right? Let's say I'm playing golf. I'm practicing how to play golf. So in golf, there is a certain swing that you have to do, right? It has to go in a certain arc. The first time you go and play golf, you're not going to be able to hit the golf ball with your club. You're going to miss. You do it hundreds of times, you're going to start hitting the ball. So you're practicing deliberately, consciously. You do it tens of thousands of times, then your swing is going to get better and better, and you're going to be able to hit the ball further and further away, and you're going to be able to ensure that it ends up where you want it to end up. That takes hundreds of hours of practice, tens of thousands of swings that you practice. You're practicing deliberately, consciously. But the subconscious mind is internalizing this, and it becomes part of your muscle memory. After a long period of practice like this, many months, years, you can wake up in the middle of the night and do a perfect swing without even thinking about it. So that's where the subconscious mind has taken over. So you practice consciously, but you execute using the subconscious mind. That is the key to sporting excellence. Now, people who get nervous, let's say you are a great golfer. You're a great golfer. You execute flawlessly in practice. But when you go for the competition, you're nervous. You're nervous because you see so many great golfers around you. You may be better than them, but if you're nervous and you're going to go do your swing, you're going to again do it consciously. The key is to turn off the conscious mind and let the subconscious take over, because the subconscious is going to execute far better than the conscious mind. So there is a whole mental programming that you have to master as an elite sports person, whether it is golfing, whether it is archery, whether it is any other sport. You have to master the mind. You have to allow the subconscious mind to take over while performing in competition. You practice consciously, you perform, you execute by allowing the subconscious mind to take over. These are two different aspects of mind. So the subconscious mind is stubborn. It internalizes things and refuses to give them up. That's why you need to consciously ensure that your subconscious mind internalizes the right things. You repeat certain negative things to yourself over and over again, it's going to have a real effect on you. There is something called negative self-talk and positive self-talk. If a person is a very positive person by nature and they keep repeating to themselves mentally, I'm great, I'm this, I'm that, whatever it is, positive self-talk, that person's self-confidence over time will grow better and better. But a person who constantly criticizes himself or herself internally all the time, that internal self-talk, you keep doing it for months, you're going to become a very diffident, low confidence person who will not perform well in life. So this is how you train the subconscious mind, through your self-talk, through what you choose to tell yourself over and over again, and the way you practice and so on. So that is kind of the difference between the conscious mind and the subconscious mind. What I'm doing right now, I'm speaking to you all, I'm doing it consciously. My conscious mind is doing it. But the habits, the behavior, the outlook, the attitude, or whatever else is there, is because of the habits that have been ingrained in me by my own choice over years. Yeah. So some people, you feel they are very positive, very cheerful, very joyous. It's because of their subconscious. I mean, you can act for some time, you can pretend, but you can't pretend forever. You cannot pretend to be something else that you are not forever. Eventually, your true nature comes out. Similarly, some people, you can sense that they are very low confidence. They are very, well, kind of negative. They have a negative aura, or whatever you want to call it. Yeah, whatever word you want to use. So that's because of the subconscious shining through at times, and so on. So yeah, there are no clear scientific definitions of subconscious, conscious, etc. But it does exist. Psychiatrists will know this, psychologists will know this, and so on. So that roughly is the difference between the conscious and the subconscious, the psyche and the actual conscious mind. Okay, Shweta says, could you critique and compare gravity, Newton's theory versus the fabric of space and time, which is Einstein's theory? Right, good question. What is the difference between Newtonian gravity and Einsteinian gravity, which is general relativity? That is a very good question, and I'm glad somebody asked. So what is all this stuff? Um, so Newtonian gravity. All right. So let's talk about gravity. Gravity. The understanding of what gravity is was the first big unification of the forces. What do I mean by that? We all knew, our ancestors knew for thousands of years. You take an apple, you drop it, it's going to go right to the ground. It's going to go towards the ground. It's going to fall. All objects, all massive objects fall. They fall downwards. We knew this. You throw a stone in a certain direction, it's going to take a parabolic trajectory, a ballistic trajectory, it's going to fall, and so on. We knew this. But the big leap of imagination was when some of our ancestors realized that the force that makes things fall on the earth is the same force that governs the motions of the stars and the planets in the sky. That leap of imagination, that realization was the first big unification of forces. The forces that govern us on this little planet are the same as the forces that govern the massive universe, the stars, the galaxies, the moon, the planets, the sun, and the earth. That was the first big unification. So our ancients called it Gurutvakarshan in Sanskrit. Eventually, these ideas made their way to the West. Calculus made its way to the West. Newton got hold of it, and he came up with the Principia Mathematica in Latin, which also had the theory of gravitation. So Newtonian gravity is what Newton came up with. We call it Newtonian gravity. And according to this perspective on gravity, gravity is a constant instantaneous force. Constant force, instantaneous force. Action at a distance. And it is represented by the equation F is equal to G times m1 m2 upon r squared. The potential is a 1 upon r potential. The force is G m1 m2 upon r squared. F is the force, G is the Newton's constant, m1 and m2 are the masses of the two objects, the two massive bodies, and r is the radius, the distance between the centers of the two masses. That is the Newtonian gravity in very brief. It's an instantaneous force. It's a constant force. It's an attractive force. Yeah, a pulling force. It's action at a distance. That is Newtonian gravity. Einstein's gravity went way beyond that. Einstein demonstrated, he theorized that gravity, this what we perceive as the force of gravity, is actually the curvature of not only space but time, the four-dimensional structure, fabric of space-time. So when you have a mass in space or space-time, the presence of the mass causes the fabric of space-time to curve, to bend, to distort. Mass curves space-time, and the curvature of space-time tells mass how to move. So it works both ways. So this is the geometric theory of gravity, geometrodynamics, which is general relativity, which Einstein came up with in 1915, and it has been tested thousands of times. The objective of all these tests is to prove this theory wrong in different ways. And thus far, all the tests have failed. This theory works. It's the best theory that we have at large distances in the macroscopic sphere of the world, domain of the world. That's the main difference between general relativity and Newtonian gravity. Another big difference is that in Newton's perspective, gravity is an instantaneous force, action at a distance, infinite range. In the Einsteinian perspective, the better perspective, there is a speed limit. It's not instantaneous. The curvature of spacetime doesn't happen instantaneously. It has a speed limit. C, the speed of light. And let me illustrate this. By going to where is the image? Once again. Let's do a thought experiment, my dear friends. I always talk about thought experiments. Let's do a thought experiment. This here is our beloved home system, the solar system. At the center, you have the sun. Then you have the different planets: Mercury, Venus, Earth, Mars, the asteroid belt, and then Jupiter, Saturn, Uranus, Neptune, and how dare they not throw Pluto? Anyway, this is the solar system, right? Now let's do a thought experiment. Let's say by magic, I make the sun disappear. The sun at the center of the solar system, I make it vanish all of a sudden by magic. Then what happens? According to Newton's perspective, gravity is what keeps the solar system together, because of the enormous gravity and the mass of the sun. If the sun were to suddenly disappear, all the planets would immediately fly off in different directions, because this great mass that is holding them together is gone. So if you were to make the sun disappear, according to Newton, all these planets would immediately fly off into outer space in different directions. Now, according to the Einstein version of gravity, the better version of gravity, there is a speed limit. If the sun were to disappear, we know that it takes light 8 minutes roughly to travel from the sun to the earth. So even if the sun were to disappear, on earth we would not know about this for 8 minutes. For 8 minutes we would still believe the sun is still there, because we are still getting the light that was emitted 8 minutes ago. It's only after 8 minutes that we on earth would realize that the sun has disappeared, and it's only after 8 minutes that the earth would start flying off in a different direction. It would take longer for that to happen to Mars, much longer for Jupiter, Saturn, Uranus, Neptune, Pluto, and so on. So it is the inner planets that would start flying off first, and slowly, one by one, the outer planets will go off in different directions once the gravitational effect of the sun disappears at the speed of light. So this is the major difference, very, very significant difference between Newtonian gravity and Einstein's general theory of relativity. And the general theory of relativity is the better, superior version. We know that. So that, in brief, is the major differences. Saurav says, how legitimate is psychiatry as a profession? I read somewhere that 1 in 7 people in India are suffering from an undiagnosed mental illness. That said, is it in any way factual or a survey meant for the big pharma's profits? Also considering the opioid crisis, which keeps coming in the news. Okay, all right. Oh, psychiatry. Well, psychiatry is kind of hand waving and voodoo. See, let's say you are an orthopedic surgeon doctor. How do you know something is wrong? You take a look at, let's say a person comes with a broken arm and you want to fix it. You're going to take an x-ray. You're going to see exactly what the affected part of the body looks like, right? Let's say somebody has kidney problems. You're going to scan the kidney. You're going to go do a whole bunch of tests, and you're going to figure out exactly what is wrong with that kidney. Let's say you are an eye specialist. You're going to look at the eye and see what's wrong with the eye, and so on and so forth. You're a gastrointestinal doctor, surgeon, whatever. You're going to do tests and do imaging of the object, of the stomach, of the intestines, etc., and then diagnose what's wrong with the person. When it comes to psychiatrists, they are diagnosing brain problems, mind problems. How do they do it? Do they ever take a look at the brain? No. Psychiatrists are the only members of the medical profession that never take a look at the organ that is affected, which is the brain. So how do they make the diagnosis? They talk to the patient. They tell the patient to lie down on a couch, on a sofa, or whatever it is. The patient lies down. The psychiatrist typically sits on a different chair next to the person, and then asks questions, interviews the person, tells the person to tell stories about their life, or whatever it is. And this happens over multiple sessions or over a long period of time. Eventually the psychiatrist makes certain assessments, tries to tease out certain symptoms or clusters of symptoms, and based on this very rough procedure, they diagnose what is wrong with the person and prescribe various medications. It is hand waving and voodoo. That's what it is. That's what psychiatry is. What should actually happen is at least do imaging of the brain. Very often what happens is that people have undiagnosed brain injuries. It happens very often. Brain injury, when we typically think of a brain injury, we see in our mind's eye a person falling down a flight of stairs and hitting their head on the floor, or a person falling from a tree and hitting their head on the ground, or a person playing American football and being hit in the head repeatedly, time after time after time, or a person playing cricket and being hit by a cricket ball. You have a concussion. So this is how we imagine a brain injury to happen. And often that's how it happens. A kid at the age of 3 fell down, was unconscious for 5 minutes, then he grew up, he was fine, and everything went back to normal. But that may have resulted in a brain injury. The person seems to be normal, the kid grows up, but over time they exhibit symptoms of mental illness. It could be because of a brain injury, but because the kid just did not appear to be ill, it was forgotten. These things happen very often. In the case of the opioid crisis, like you mentioned, drug abuse, etc. Drug abuse damages the brain. Long-term drug abuse, whatever drug you're using, hard drugs, whatever it is, it ends up damaging people's brains. But that is never seen. It's never visible to anyone. The person looks just fine. So I would say that psychiatrists should add certain tools to their arsenal. They should do brain imaging. There is something called SPECT imaging, SPECT, single photon emission computerized tomography. SPECT imaging should be done, which essentially gives you a good scan of how the brain is. What are the regions of the brain that are active, that are showing more activity? Which are the ones that are showing less activity? Is there any damage in the brain and all so on? You can see that. So that would actually give you an idea of whether a person actually has any brain injury, or whether there are regions of the brain that are hyperactive. There is something called OCD, obsessive compulsive disorder, in which the brain refuses to calm down. You have parts of the brain in the frontal lobes that are hyperactive. Typically, in a healthy brain, the back of the brain needs to show more activity. The front and other parts of the brain should be showing low activity. In OCD, you have the frontal lobes, etc., that show very high activity, and so on. So if you do this sort of imaging, SPECT imaging or whatever else, then you can get a good idea of what's actually happening. Because sometimes you have people which show the same symptoms, but they have very different brain scans. So what needs to happen is that psychiatry needs to actually use some imaging techniques. Psychiatrists need to be trained in all of these things. They should be trained into how to read brain scans, what brain scans to prescribe, and then based on this more solid observational data, scientific data, on the basis of that, they should make their diagnosis and they should prescribe medicines. Right now, it's all voodoo and hand waving. They sometimes prescribe behavior therapy that can be very cruel. Someone's suffering from a brain injury which is exhibiting itself in a certain range of symptoms, but you are prescribing behavioral therapy to correct the behavior. The behavior is an outcome of the injury. You have to treat the injury, not the symptom. So that's how it is. Right now, I would say psychiatry is just hand waving and voodoo. I do not even consider it to be science. That is my assessment of psychiatry. It is not science. It is hand waving and voodoo. That's all it is. An amazing Indian citizen says, why has India lost the speed in the global supercomputer race? India has never really invested in supercomputing. I think if you look at I don't know what the rankings are right now. If you look at the top 100 supercomputers in the world, I think India would have 2 or 3 of those in the 90s. So India has never really tried to participate as a serious player in this big race. Most of the top 10, top 20, top 30 supercomputers will be American, Chinese, or maybe Japanese. Maybe a couple of British and French supercomputers, maybe something from Israel perhaps. But the top 3 major players are the US, China, and Japan. India is not even trying to participate. And it's not that hard to build a supercomputer. You can build a supercomputer on the cheap if you know how to do it. You have to cannibalize existing computers. So what is a supercomputer? So a supercomputer is a very powerful machine computer with extremely high processing power, parallel processing, very high flops, teraflops. What's a flop? Floating operations per second. Teraflops is it in the 10 raised to what? Megaflops is 10 raised to 6. Gigaflops is 10 raised to 9. Teraflops, petaflops, and so on. So very high processing power, right? That's what it is. Like I said, it's possible to build yourself a supercomputer on the cheap. All you have to do, you have to spend some money, of course, but not the kind of billions of dollars you would imagine. All you have to do is, you know what a PS5 is? PlayStation 5. A PlayStation 5 has extremely high processing power. Buy 1,000 of those. Yeah, it's expensive, but it's not as expensive as building a supercomputer. Uh, what does a PS5 cost? 50,000 rupees. You buy 10 of that, it's 5 lakh. 100 is 50 lakhs. So 1,000 of these would cost about 5 crore rupees. You take them apart, take the processors. You need to do some hacking, some black magic, obviously, computer black magic, and you tie these processes together. You bring them together and make them process in parallel. There you have your own supercomputer, a very powerful supercomputer. So it's been done. People have done this with the PS2 20, 30 years ago. 20 years ago, PS2 was one of the older versions of the PlayStation. It was possible to take 100 PS2s together, piece them together, and create a supercomputer out of that, a very good supercomputer. So it's possible to do this on the fly, on the cheap. I say, why can't the IITs have a yearly budget and a yearly competition? The Indian Institutes of Technology, which are currently investing in the humanities for whatever reason, eliminate the humanities departments. IITs are for technology, not for humanities. Use that money, invest it in a yearly competition. Uh, every IIT gets a certain amount of money, a few crore rupees, to build their own supercomputer. Yeah, you have 1 year every year to do this, and then at the end of the year, we're going to compete. Which supercomputer among all the IITs has the best power? The best is the most powerful, and then you get a big prize, and you can start your own startup or whatever. Why can't we do that sort of thing? It's not that expensive. It takes a little bit of leadership and vision, which we are currently lacking. Our IITs, our all the entire academic system is run by people with a bureaucratic mindset, people who want status quo, people who are not ambitious. Unfortunately, that's what's happening. We have the money in the country. We have the money. It's just the mindset that's problematic. It will take a little bit of leadership and a little bit of ambition to change this entirely. And of course, now we have AI, we have machine learning, we have neural networks. We can use all that on supercomputers. We also have quantum computing. I don't think we are doing anything in India vis-a-vis this new emerging field of quantum computing. Quantum computing is not that easy. You need extremely low temperatures to have a quantum computer, because you need to create quantum superpositions and sustain those superpositions in order to do quantum computations using qubits. So that is a different field. You need cryogenic temperatures for that. So at least, I mean, that also should be certainly invested in. I think there was some initiative, but the amount of money they were putting into it was laughable, unfortunately. So India can still become a major global power in supercomputers, in quantum computing in the next 10 years, provided we have the right leadership and the right attitude and the right ambition, and we do some restructuring of our academic institutions. It's very much possible. It's still possible today. Let's see. Chetan says, since we humans aren't centrally connected, how is it that we all have unique fingerprints and DNA apart from identical twins in some cases? Is it possible that two people can have the same fingerprint? I'm not sure how fingerprints are created. I think I don't think there's an exact code for your exact precise fingerprint in your DNA. It's something that happens. I'm not sure what the biological process is that gives rise to everyone's unique fingerprints. What we do know is that fingerprints are reasonably unique. 1 in 10 million. So if you take 10 million people, the probability is that roughly maybe 6 million, maybe 4 million, maybe 10 million. I'm just giving you a ballpark figure. So the probability, let's say it's 10 million. So the probability is that if you take any random 10 million people, let's say, all of them will have unique fingerprints. But if you take 20 million people, maybe 2 of them will have fingerprints that match. So I think, and the same goes for DNA. DNA fingerprinting, the old term for the technique. So if you have a population of 7, what is the population of the earth now? 7 billion. Some people will have fingerprints that match, and some people will have DNA that match. So let's say the chance is 1 in 10 million. Then in a country like India with 1.4 billion people, there could be 140 people that have the same DNA as me and the same fingerprint as me. It is possible. And if you look at the entire population of the world, you have to multiply by a certain figure, and you will come. So DNA is not entirely unique. It is possible that people just randomly may have the same DNA and the same fingerprints. It is possible. Statistically, it is possible. That's all I can offer you. I'm not sure how exactly it happens that your unique fingerprints are created. I'm not sure what the process behind that is. Maybe if you look into the biological uh, dynamics mechanics of this, you may get an idea of how it happens. Udit says, what would be the reaction of space core from different countries if they found multicellular organisms on other planets? I think only one nation that I know of has a space core. That is the United States, a space force, which is a branch of the U.S. military. The U.S. Space Force was created on the orders of the 45th president, Mr. Trump. I'm not sure if the Chinese have a space force, space corps, whatever you want to call it. If they do, then maybe two countries have it. India doesn't have a space force officially, and so on. So let's talk about what would be the reaction from the scientific community in different countries. Let's say we find unmistakable, undeniable evidence of multicellular primitive microorganisms on, let's say, Titan, or let's say Enceladus, or Europa, or Pluto, or maybe Mars, maybe Venus. What would be the reaction? Firstly, not a great deal of surprise, but very high amount of excitement. That would be incredible. The first time in human history we have discovered this. So the excitement levels will go through the roof. Surprise, not so much, because I think it's quite likely, if you from the biological perspective, it's reasonably likely that there could be primitive microbial life on these various parts of the solar system. So multicellular organisms like microbial animals, that would not be a great cause of concern. That would not cause a great amount of surprise. It would cause great excitement. And microbial life doesn't pose any kind of threat to our planet, to our species, to our ecosystem environment. So yeah, it would not cause any major concern. Yeah, but yes, it would make us see the universe in a whole different light. That yes, now we know there is life apart in places other than the Earth, which could indicate that life is quite common. So I think it could perhaps be a matter of time that we detect something in the next half century, 100 years, maybe in our own solar system. It's possible. It's possible there could be microbial life. Intelligent life is a whole different thing. That would set off all kinds of alarm bells. Intelligent life is potential danger. You have to treat it as a potential danger. Let's say you're walking in a forest in the middle of the night, complete darkness, and you see somebody approaching you. What's going to be your initial reaction? Fear. Your hair will stand up. Goosebumps. Your immediate reaction is going to be fear, unless you don't care for your own survival. Because in the dark forest, when you see something approaching you, you have to assume it's going to be a threat to you. That's the only way you can ensure a survival. That's the dark forest theory or worldview, which says the entire universe is like a dark forest. Everyone's hiding because they know any potential intelligent life that you encounter could be a mortal threat for you. So if we discover microbial life, multicellular organisms, it's not going to be a cause of concern. If you detect signs of intelligent life, that is incredibly dangerous. So whole different perspective. But yeah, you discover life, even microbial life, it tells you there's a high likelihood that there could be more evolved life in other places, which again should elevate your threat status. Akash says, do you think coding, programming is becoming or will become an absolute skill in the near future? I've seen experts on both sides of the arguments. Some claim that it's an essential skill that should be taught to every child right from an early age, just like math. Others say this idea is being blown out of proportion. I think the reaction and the response and the kind of argument that you see depends on the age of whom you're asking. Older people will typically say it's not important. Younger people will say it's an integral part of the future. So how do we see this? It depends. Are computers going to be around forever for the foreseeable future? Yes. Are most problems in the world now being solved via computers and via programming? Yes. From that perspective, one would have to say that yes, coding, programming is going to be important, quite important. It's a skill that is as easy to learn as mathematics. It's just logic in a certain way. Obviously, some people will have a better aptitude, some people may not be so good at it, naturally inclined to that, and so on. But as long as computers are going to be a part of the future, as long as more and more problems are going to be solved through programming, through coding, through computers, through software, as long as that sort of future is in the offing, I think coding and programming is something that we need to inculcate in children who want to do well in life. Uh, of course, manufacturing and all those other skills are also important. Without that, you cannot build computers and so on. Research is important. But when it comes to problem solving, it's all about solving problems. Today, many of the world's problems, many of society's problems can be solved through computing, through computers. So as long as that happens, coding and programming is going to be very important. So I think we can all envisage a world in which computers become more and more an integral part of our life. They become ubiquitous. We will have augmented reality. We'll be able to wear glasses that show us a whole lot more about the world that we can see right now. If that future is the future, which it seems to be, then then programming and coding is going to be important. So I think that yes, it is a good bet from my perspective that programming and computing is going to be an essential skill. If you want to do well in life, you need to have that in your skill set. You may want to be a philosopher, you may want to be a poet, you may want to be somebody who tinkers with physical equipment, or you maybe want to be a teacher, etc. Even in those occupations, programming could be an asset. So yes, overall, I would agree with the camp that with those who are in the camp that says that programming and coding is important. It's going to be a very, very valuable skill in the future. So yeah, I agree with that. Saurav says there's a big debate about what depression actually is, whether it's a mere chemical fluctuation or something deep rooted, which also involves sociological factors. Do Indian medical systems like Ayurveda have definitions of depression and other psychiatric illness in general? Depression could have a physical cause, like I mentioned some time ago. Somebody has an undiagnosed brain injury, somebody has a tumor that's growing in the brain, somebody has a cyst in the brain that can affect the brain chemistry, the brain functions, that can cause very strange behavior or abnormal behavior that can manifest itself as depression or something worse. Yeah. So yeah, that can have chemical causes. On the other hand, there are people who have completely normal uh, brain function that also have depression. What is the cause of that? There are certain scientists who like to say that all emotions and thoughts are chemical reactions. That is a hyper simplistic and idiotic view of the world. We don't understand anything about the brain. We understand next to nothing about it. We don't know where consciousness comes from. We don't know really where emotions come from. Yes, it's possible to modulate emotions using chemicals. There are certain drugs that are available for depression. I'm not sure what it's called. Prozac, is it? And there are things like DMT, like LSD, that cause various brain reactions and feelings of euphoria and so on. These are drugs. So yes, you can certainly change the mood, emotions, well-being, mental well-being, emotional well-being using chemistry, using chemicals. But that doesn't solve the long-standing problems that a person may have. So we don't know what depression is. We don't know what it is. But there is something called schizophrenia, paranoid schizophrenia, all kinds of mental problems. Some of them could have a physical cause, an actual cause. Alzheimer's disease is obviously a deterioration of the brain tissue. But yeah, it's still something that's not very well understood. I would disagree that everything is about chemistry. I don't agree with that. Do Indian systems like Ayurveda have definitions of depression? I am not sure about that. We have lost a lot of our information and data about Ayurveda. So yeah, we don't know much about this, unfortunately. But I would not agree. There is no clear definition of depression. Maybe depression comes in various there could be multiple causes of depression. Uh, Sometimes depression is caused by external factors, the circumstances in a person's life. If a person sees no hope, is trapped in a hopeless situation, that can certainly cause depression, the loss of will to live, and so on. So it has multiple causes. There could be chemical causes, there could be physiological causes, there could be external causes. It's a very complex topic. So that is what I can say about this. Right. T1 says, does India need more computer science engineers or more physics professors or physicists? Very nice way of putting me on the spot, yeah? Look, India needs more engineers, whether it's computer science engineers, whether it's actual civil engineers or whatever other engineers. Progress happens through technology. Technology is developed through engineering. The concepts are what comes out of physics. The conceptual breakthroughs, quantum mechanics, relativity, which is all being used in various technologies today, that came from theoretical physics. So all the major conceptual breakthroughs happen through theoretical physics typically. Then it makes its way into experimental physics like nuclear physics, nuclear reactors and all, and eventually technologies come out of it and they spin off into the civilian sphere. So typically, theoretical physics is about 50 to 100 years ahead of any actual engineering application and technological application. Without physicists, these things can't happen. But the actual work of bringing this technology to the society is done by engineers. So maybe we need 1% physicists and 99% engineers. Or maybe 2% physicists and 98% engineers. Engineering is something that doesn't take a lot of, well, what's the word to use? Intelligence. Maybe you do need to be very intelligent to be engineers as well, but yeah, it's a certain aptitude. And typically they kind of so I would say 2% physicists and 98% engineers. That's what the world needs, and that's what India needs. India needs a lot more engineers to build the nation all over again. Yeah, right. What else do we have? Yash says, what's the difference between intuitive understanding and mathematical understanding? Is mathematical understanding opposite of intuitive understanding, where we cannot apply one and use the other? There are two kinds of scientists, two kinds of mathematicians. There is one kind of mathematician who takes a big problem and he or she uses the entire toolkit of mathematics at their disposal to kind of try and solve the problem. Use differential equations, use linear algebra, use whatever else, matrices, whatever, number theory, and so on, Galois theory, whatever. You use the entire toolkit, the entire corpus of mathematical knowledge that you have, and you try to make progress towards solving that problem. That is mathematical understanding. Logic, pure logic, codified in the form of mathematics. There's a different kind of mathematician as well, a very rare kind of mathematician. They see the solution first, and then they know what the solution is. It appears to them in their mind's eye, intuitively. Ramanujan used to say that it was his goddess, Namagiri, who used to come to him in his dreams and give him these incredible equations that people are still researching. So there is this, and there was somebody like John Forbes Nash, the great Nobel Prize winner who won a Nobel Prize in economics for the Nash equilibrium. He was that kind of a mathematician. He also unfortunately suffered from schizophrenia for some time. So there's this very rare genius level mathematician who sees the solution, the answer first. They know it's right, and it's always proven to be right eventually. They see the answer first, they write it down or whatever, and then they have to spend weeks, months, maybe years figuring out the mathematical proof that proves that their answer is correct. That is the difference between intuitive understanding and mathematical understanding. Intuitive understanding is all about flashes of insight. Wow, oh yeah, that has to be true. I know it's true. My gut tells me it's true. And then I have to find a way of actually proving it through mathematical logic. Right? That's the difference. Okay, let's take a couple of live chat questions. We are almost at the end of today's thing, today's session. If you have questions, let me know in the live chat. Questions about science, technology, etc. Okay, there's an interesting perspective here. Not intuition, but seeing patterns and putting those patterns together on paper. Intuition comes from internalizing a lot of patterns. You don't become a genius level mathematician just because you're born intelligent. You have to spend hundreds of hours, thousands of hours studying mathematics. When you spend hundreds and thousands of hours studying mathematics, solving problems, those mathematical patterns that get ingrained into your subconscious mind, and that's how you earn those genius level flashes of insight, because of all the patterns you have internalized. That is also your intuition. You go somewhere, you know something is wrong, get out of here. That's also intuition. You cannot see something is wrong, but it's your ingrained ability to recognize patterns that tells you that something is off in some situation. So yes, it's about patterns, but you have to earn the ability to recognize those patterns and to gain those flashes of insight through incredible amounts of hard work. Right. Um, what's the God particle? It's not a particle that came from some God. This term, the God particle, was coined by some science journalist or some journalist. The so-called God particle is the missing boson, the Higgs boson that imparts mass to the universe. So its existence was theorized maybe 50 or so years ago by Peter Higgs, and particle physicists have been searching for it ever since. And it's only in the last decade, in the past few years, that it was actually discovered in the Large Hadron Collider. So it is, in quantum field theory, every fundamental particle has its own field. It's, let's say you have protons. Protons are essentially nothing but excitations in the proton field. Electrons are local excitations in the electron field that permeates the entire universe. The protons in my body are part of an infinite field that permeates the entire universe, and it is the field of the protons. Similarly, there is a Higgs field that permeates the entire universe. And the particles that interact with the Higgs field, or the Higgs boson, which is a local excitation of that field, the particles that interact with the Higgs field acquire mass. And the particles which are unable to interact with the Higgs field remain massless. That's the Higgs field, the Higgs particle, the Higgs boson, and that's what some journalists, I believe, called the God particle. So now everyone thinks it's some supernatural thing or something. No, it's not. No, it's not. Okay, let us take maybe a couple of questions more. Is our universe in an atom? Is our universe is One could think of it as some kind of atomic thing, yeah, possibly from a certain perspective, possibly. Some people ask whether the universe is a black hole. We are all inside a black hole. Well, there are problems to that sort of scenario, because first of all, the universe is expanding. If you have a black hole, it's not expanding. Yeah, we have the expansion of the fabric of space-time. We know it's happening. Inside a black hole, there is no such process. So that's our thing. And once again, the atomic thing is also one interesting way to look at it if you are a high school student, but not quite. Okay, is there any other interesting question? Grandfather paradox. Look at one of my previous episodes. I have gone into that in detail. Do a live session. This is a live session. We are live. Hello. This is live. I'm talking live. This is not recorded. Maybe you're saying video session. Is that what you're saying? Well, that is problematic. Why are video chat sessions problematic? Because firstly, I don't get to select the questions. So very often you have questions that have already been answered lots of times. People ask me all over again. So that doesn't provide value to you, the audience. It provides value to the person who's asking the question, only to one person. My intent in doing all of this is to provide some genuine value to as many people as possible. I can do that by picking new questions each time. In these video chat sessions, what happens very often is that I get repeated questions that have been answered many times. Secondly, some people want to ask multiple questions. They want to spend as much time as possible on the screen with me. I have nothing against that, but I want to give a chance to as many people as possible in as short a time as possible. So it doesn't always work that way in video chat sessions. So that's why I have stopped doing that. Maybe I will bring that back again sometime in the future. If all of you want it, I can do it. Do you want it? Let me know in the comments below. Not in the live chat, in the comments below once this session is over. All right, with that, I think we should bring an end to the session. We have again crossed 2 hours. Always fun answering all of your questions. I did a Twitter session day before yesterday, I think. That was great fun. A lot of questions, a lot of interesting questions. So maybe I will do that again next week, a Twitter session in which I will answer your questions through tweets. So that brings us to the end of today's session. Thank you very much, all of you. Great talking to you all. And I will see you in tomorrow's session. Until then, thank you. Take care. Bye.